All right. Okay. Hi, everyone. So I want to first recap what we've done in the past couple of lectures, and then we'll move on to a new topic. I'm not sharing my screen, am I? So basically, again, kind of, if you what does it mean to analyze for complexity? It means say what the runtime will be proportional to. So why do we say what is it going to be proportional to? Well, because basically, if you take a program and you take another program and you run both sets of programs on one computer. So we have the runtime for program A and the runtime for program B. And then we do the same on a second computer. Then in general, it's going to be the case that if computer 1 is slower by 15%, 50% than computer 2, then the ratios are going to be the same, right? So if computer 1 runs at 50% the speed, then that means that this will be half of this. And similarly, this will be half of this. Right? So if we know that the runtime is proportional to f of n, where n is length, quantity, magnitude of input, then on computer 1, runtime will be c times fn for some c. And then on computer 2, the runtime will be c1 times f of n for some c1. Right? So knowing f of n tells us kind of how fast the program is going to run. Does that make sense? So, okay. So then usually what we say is we want to say worst case asymptotic runtime complexity for input of size magnitude n. And usually it's written something like O of n squared. So this means that in the worst case for input of size or of magnitude n, the runtime is going to be proportional to n squared. So on any particular computer, there's going to be some kind of constant using which you'd figure out that for a large enough n, so that's the asymptotic part. So for n that's large, we don't care what happens for n that's small. For the worst case, assuming that the input is still of size of magnitude n, the runtime is going to be proportional to n squared for some kind of constant of proportionality. So that's the kind of thing that we mean. Make sense? So what are the different things that we saw so far for those kinds of analyses? So usually for programs with loops, you have something like this. You have for, or you have while something something, and then you have for or while something something, and then you have block of code. And then you say, okay, so assuming that this runs 1 times, and this runs 2 times, and assuming the block runs in constant time, the runtime is O of K1 times K2, or something like this. If it's nested more, then it's going to be like K1 times K2 times K3 and so on. So the block might not run in constant time. If the runtime depends on that. So the most obvious way in which it would not run in constant time is if the block is like for I in range n or something. That's if the block itself includes a loop. Well, like that's this kind of situation with for/while rather than a situation where the block runs in constant time, right? So usually if the block itself contains a loop and the loop depends on n, so something that's to do with the input rather than something that's constant. Of course, if you say for I in range 10, that's constant, that's just 10 times always. Then you have to do something different, right? So a slightly more interesting case would be something like you're doing like A is 10, and then you're doing like while I is smaller than 10, you say like A is equal to like A times A. So that we said, well, it looks like it's constant, but it's not really because integer multiplication will take longer if the integers themselves are bigger. And that's because the integers can be very large. Obviously, if you have like one integer that's like 1,000,000 digits and another integer that's 1,000,000 digits, multiplying them together can take a long time. So we specifically know that that's not the case with floats. So if you do an operation on two floats, that's constant time. So integer operations are not necessarily constant time. And I say not necessarily because you can say, well, like if you happen to know that all the integers are like smaller than a certain size, then you can treat them as if they were floats. So on the exam, I basically avoid this situation unless I specifically want to test people on a situation where it happens that you can do something. I just make everything floats. And that's because in general, analyzing this can be quite difficult. All right. So that's one kind of situation that we saw. So another kind of situation that we saw was something like, so for whatever, and then in here we have for another whatever, and here we have a block. And that was the analysis for counting sorts, right? So what happened there was that this was constant time, but this varied for different inputs, right? So the trick that we used was to say in total how many times the block ran if the situation runs for variable amounts of times, but in total the number of iterations is known. Right? So that was the situation for counting sorts last time, where we were able to say, well, like this is going to be a different amount of times every time, but in total, we know that this block is going to run some constant number of times. So that's a situation that sometimes happens. Another situation that sometimes happens is there is a formula for how many times this runs. So that was the situation with the arithmetic series where we knew that it runs n times and then n-1 times and then n-2 times and so on. And there is a formula for n plus n-1 plus n-2 plus n-3. one last thing. One last thing is a situation that's kind of like that, where we say something like while n is greater than 1, and then we should just say like divide n by 2 every time. So for this kind of situation, we know that if you start with n and you divide by 2 every time and you go down to 1, that's log 2n. And that's because you start with n, and then it becomes n over 2, and then it becomes n over 4, and so on. And then eventually it gets down to 1. And we could just think about it as going backwards. So this is 2 to the 0. And then this is 2 to the 1 from the bottom. And then eventually you get to 2 to the k. And you just say, well, 2 to the k is equal to n. It must be, because we wrote it down this way. So that means that 2 is, so log 2 to the k is equal to log 2 of n. And that means that k is log 2n. Make sense? So if it's a situation like this, then you can analyze this as this is approximately log 2n iterations. Right. So I think the examples that we saw so far, like necessarily they look kind of, it's a new thing every time. Well, that's because like, why would I repeat the same thing with like a different case here? Like that would be boring. But at the same time, if you look it over and you just kind of write down, okay, like we have this kind of case, this kind of case, this kind of case, this kind of case, when you come to the exam, well, like basically, unless it's an extremely challenging question, which is intended to be like the challenging question on the exam, well, it's going to be one of those cases. So your job is to just figure out which one it is. So what I would suggest is looking over the examples that you have in your notes from lectures and just categorizing them as like, this was this trick, this was this trick, this was this trick, this was this trick. So that then when you're on the exam, you can just recognize which of the problems it is. In general, like there is not like an easy solution to those kinds of things. Like if it's like an arbitrary problem, it might be an open research problem as far as what's the complexity of a particular piece of code. It can be quite difficult. It probably would not appear on the exam if it's a research problem. So similarly to kind of like integrals, like most of them, you just cannot do at all. So if it's on your calculus exam, that means that it's doable. Well, probably. So okay. So this is this. Questions? All right. So I now want to introduce a new topic, which will be necessary in order to get to our end goal for the next couple lectures, which is implementing an efficient sorting algorithm like what's implemented in Python. So that's recursion. So recursion just means functions using themselves as helper functions. So the classic example of a recursive function is something that's maybe kind of boring, but I might as well start with this. This is n factorial, which is again 1 times 2 and so on times n. So we saw it in a different context just now. So one way to do it is to, of course, just write a for loop. Another way of doing it is to say, well, like if this is n factorial and I'll add n minus 1 here to be explicit, well, you can write it out as n minus 1 factorial, so 1 times 2 and so on times n minus 1, and then times n. Like so. So when you're writing the factorial function, what you can say is, well, in order to compute factorial of n, if I knew factorial of n minus 1, then I would almost know the answer. I just need to multiply back by n. And now I can return. Right. So this is using the help of using itself as a helper function. Now, here you might say, well, what happens if n is 1? Well, you'll just call factorial of 0 times 1, and then what happens if you try to compute factorial of 0? Well, that's like factorial of minus 1 times 0, and that's like maybe 0, maybe factorial of minus 1, which you don't even know what it is. So recursion needs a base case. So we need to say, for example, if n is equal to 0, then we return 1. So the basic structure here in the recursive function is you need a base case. So return value for a simple input. And need a recursive step. So using the function itself as a helper function. Usually for a simpler input. So what we mean here by simpler is, well, like n factorial for a large n, that's very difficult, but n factorial for n equals 1, that's like nothing, right? Because that just, well, like 1 times factorial 0, and that's easy. Make sense? So that's it. That works. So one way to understand it is as a sort of, and this is referred to as the leap of faith. If the function works for the base case, and it works, assuming it works for simpler cases, it will work in general. Right? So we're saying, well, like this formula is right? So like n factorial is equal to n minus 1 factorial times n. That's just math. And then and it works for the simple cases. So it's like, well, if it works for n minus 1, it's got to work for n just because of the formula. And then eventually it'll get to the very simple case. So it works for smaller cases too. So it works in general. So another way to put it is if the docstring is right. Well, the docstring is right. So that means that this is correct because this computes factorial n minus 1. And the formula is correct. So, and we use the correct helper function. So it must work in general. So, of course, it wouldn't work if you didn't specify the base case. The other way to understand it is to just write out what it looks like. So this is called the call tree. Representation. And that looks, so that's just the name. And that looks kind of like this. So we're saying, I want to compute factorial of n. So in order to compute factorial of n, what am I going to do? I'm going to compute factorial n minus 1, and I'm going to multiply it by n. So when I'm computing factorial of n, I'm going to say, compute this. Once you've computed it, multiply by n, and you're done. So here it's going to look like this. And then inside of factorial n minus 1, you're going to say, well, I need to compute factorial n minus 2. And so on. And that's going to keep going until you get to factorial of 0. Right? Because it just keeps going. So like in factorial 2, it's going to say, I need factorial of 1, and I'll multiply it by 2. So eventually it gets to factorial of 0, and when it's at 0, you know what happens. It returns 1, because just this guy runs. And you get to return 1, and you're done. So that means that that will return 1. So that means that in here, it now has 1, and that will return 1 times factorial of 0, which is 1. And then here, factorial of 1 was called from factorial 2. So that will return 2 times 1 times 1. Because factorial of 1 was 1 times 1. And factorial 2 returns factorial of 1 times 2. And so on. So at this point, what's going to happen? Well, this is going to be returning back factorial n minus 3 times n minus 2. And this is going to be returning factorial n minus 3 times n minus 2, also known as factorial n minus 2 times n minus 1. And that means that this is going to return all of this mess times n, which is equal to n. Make sense? So we start with factorial of n. Factorial of n calls this as a helper function. And this calls factorial n minus 2, and so on. And then it eventually gets to factorial 0. In order to see what that returns, we just say, well, factorial of 0, we know what it returns. It returns 1 just because of this statement. So now we definitely know what factorial 1 returns, because factorial 1 returns factorial 0 times 1. So that's what happens here. So now I can say, well, what does factorial 2 return? Well, factorial 2 is factorial 1, which we already know what it is, times 2. So if you just go through this process, what does factorial n return? Well, something like this, which is what we needed, which is n factorial. Make sense? So, okay. And this is kind of very easy because in a way, kind of the math told you how to write it, right? So the math just says, well, like if you can decompose n factorial into this kind of deal, well, you can write it as a recursive function. So I want to now give examples where it's not as obvious. So let's say that I want to do print the list L. Right? And so without just print L and without loops. So again, the rules of recursion are need the base case. Did you do the don't push in a rope yet thing? AKA don't push in a rope. and need a recursive step. So that would be, of course, to know the answer. You must first get the answer or know the answer. How to get the answer, you must first know the answer. The third one is just F equals MA. Anyway, so but those are really analogous, right? So the recursive step is how do I get the answer to the whole problem by getting the answer to a slightly less complicated problem. And this is what's like the simplest possible thing on which I can kind of build the foundation of the answer. So, okay. So here's what we're going to do for this. So the base case will be if the length of L is 1, can just print L0. That prints the entire list. The recursive step would be first print L0 and then print the rest of the list. So we're going to say, okay, so if the length of the list is 1, we'll print L at 0, and we're done. If it's not 0, what we'll do is we'll print L at 0, and we'll print the rest of the list. Right? So the base case is if the length is 1, then that's simple. We just print the first element. Otherwise, we'll just print L at 0. And then we'll print the rest of the list. And we'll print the rest of the list by using the function itself as the helper function. And again, if the docstring is right, then this must work, because if you first print L at 0 and then you print the rest of the list, well, you've printed the list. Make sense? So here, let's try it. So we've printed 5 and then 6 and then 7. Okay, so why did that work? Again, we're going to say you start with 5. So you start with print list track 5, 6, 7. So we go in here. So the length of the list is not 1. So that means we print L at 0. So this means that this will print 5. And then it'll co-print list track with 6 and 7, with L starting from 1 and up to the end. So when you co-print list track with 6, 7, what happens? Well, the length is not 1, so we're not here. So we print L at 0, so we print 6. And we call print list track with the rest of the list, with just 7. What happens here? Well, the length is 1, so we print L at 0, we print the 7, and we return. So the way we drawn it out is we printed 5, and then we printed 6, and then we print 7, which is exactly what happened. The mathematical way of looking at it is, well, if the length of L is 1, this is definitely right. all we do is we print the first element of the list. And then we return, so we're done. If the length is not 1, well, we print the first element, and then we use this function, which, according to the docstring, prints the list, and we print the rest of the list after we printed L at 0. Well, you print L at 0, and you print the rest of the list. That's printing L. Make sense? So, okay. So here's something that's kind of interesting here. You can print the list in reverse in a very similar way. So let's say that you want to print the list in reverse. Well, how would you do it? So basically, again, let's think about it mathematically. So to print well, one way to think about it is we can say print everything in reverse and then print L at 0. So first reverse the rest of the list and print that, and then print L at 0. So definitely L at 0 should go at the end. What should be before L at 0? Well, the reverse rest of the list, except for L at 0. Right? So if you think about it in terms of 5, 6, 7, what would that be? Well, the last element would be 5, and then reverse this, put it at the start. That's what you need to reverse the whole list, right? So that would be 7, 6. So, okay. So we'll do the same thing. So I'll say if the length of the list is 1, I'll just print L at 0 because a list of size 1 reversed is just itself. And I'm done. Otherwise, what I'll do is I'll print the rest of the list in reverse. So that's all of that reversed, print that. And then I'll print L at 0. Right? So mathematically, that should work. Mathematically, this is saying, well, in order to print the entire list in reverse, what do you need to do? Well, reverse the rest of the list and print that. And then at the very end, print L at 0. Right? So that's got to work. So in terms of like, how would it actually go? Well, let's think about it. So let's say that we call this function with 5, 6, 7. What's going to happen? Well, we are getting to this point. We haven't yet printed L at 0. But first we need to finish with this. Only then we will get to line 42. So what would happen is we're calling the function with 6, 7. And similarly here, you try to print 6, 7 in reverse. Well, you get to this line, and this is saying print the rest of the list, which is just 7 in reverse. So we call it like so. And then here we'll print the 7 because to print 7 in reverse is to just print 7. Here, we are done with this. And now we'll print 6. So that would be the print L 0. And here we'll be at print 5. So you'll notice that those two trees are actually, the call trees are actually the same. They look the same. The difference is the timing on when things got printed, right? So what happened here was we first called this, then we got to here, then we got to here, and here we printed the 7, and then on the way down, so when we called print list reversed recursive, we called it with 6, 7 at some point. This resulted in the 7 being printed, and then we got to here and we printed the 6. When we called the function with 5, 6, 7, what happened is we first called print list reverse track 6, 7. That printed 7 and then 6, and then we got around to printing the 5 because that's the order, right? So L is 5, 6, 7. Well, this is going to print 7, 6, and then this is going to print the 5. Would it print L0 twice? Well, no, because of the return. So the return says you're done with the function. Okay. So kind of the way we designed this was just mathematical, right? So we just said, so in order to print the list in reverse, first print the rest of the list in reverse and then print the first element. On the other hand here, in order to print the list from forward to back, well, just print L at 0 and then print the rest of the list. But it turned out, well, at least if you set it up this way, that all you needed to do is just change the order of the lines, and that resulted in backward instead of forwards. So, okay. Questions? Yeah.
So another way of doing this, having it written this right,
Yeah, sure. Yeah, so you could also just get the last element, so print the last element and then print everything else. Yeah. It's just that I wanted to do this kind of like switch, but you're completely right. So like another way of doing it is, so again, you have to have some kind of base case. And by the way, you could also do like his length 0 as well if you wanted to. So you could say print L minus 1. And then print reverse everything up to L minus 1. That's also possible. Make sense? All right. So basically so we'll do it in a more kind of comprehensive way next time, but you can, so this of course you could also do with a for loop if you wanted to. And there is a procedure for converting between for loops and recursive functions. For now, I'll just do an example. So let's say that I want to compute a to the power of n. So one thing I could do is I could say, well, just multiply by a n times and return the result. Another thing I could do is I could say, well, a to the power of n is equal to a to the power of n minus 1 times a. So that's very similar to the factorial formulation. So then I could just say, so this would be a to the power of n, and I'll just say, okay, so what's the base case? Well, that's like the simple situation. If n is equal to 0, I know the answer, right? So if n is equal to 0, I'll just return 1. And otherwise, I'll return a times power rec a n minus 1. Right? So this is basically just saying a to the n is equal to a to the n minus 1 times a. Let me put the a here so that it's nice. Right? So a third thing I could do is I could say, well, the structure of this guy and the structure of this guy, they're not really the same, right? So here I'm just doing kind of like a times a times a times a. And here I'm using this a to the n is equal to a to the n minus 1 times a. So what if I didn't have this insight? Could I still do this kind of deal using recursion? And the answer is yes, I could. So here's what I could do. I'm going to say, okay, so first of all, let me rewrite it as a while loop. So, and that's kind of like part of how you would think about it so that you can think about it recursively. So instead of for I in range n, I'll say I is equal to 0. And then I'll say here, instead of this, I'll say while I is smaller than n, I plus equals 1. So that's kind of like just a small change to make it not a for loop, which is difficult to transform. Right? So you see how it's the same because I is 0, then 1, then 2, and so on. So now what I can say is, okay, all right. So I want to keep track of res and I want to update them recursively rather than iteratively. So what I'll do is I'll say, okay, so I need a, I need n, I need I, and I need res. And you'll see the transformation in a second. So here, when do I return? I return res when I becomes equal to n. So I'll say if I is equal to n, just return res. Otherwise, I'll say, okay, so I need to return this kind of thing. So the analysis would have to wait for Wednesday, but I need to return this. So A is the same, N is the same, and then I becomes smaller, and res becomes res times A. So what I'm doing here is I'm saying, okay, like if I is equal to n, then I'm done. In the same way that here, when I is equal to n, then I'm done. And I just return res. Otherwise, I'm saying send A to A and send n to n and send I plus 1, sorry, to I. So the next time I is going to be I plus 1, and then send res times A to res. And that's the same structure. This, we'll get back to it next time. I'll see you. Bye.